Kumar Deepak, a distinguished engineer in Xilinx in the data center group at Xilinx. He has over 20 years experience with Xilinx in architecting and developing large-scale complex software and hardware systems. And currently he's leading development of solutions for accelerating data analytics and using Xilinx FPGAs. So Kumar, I'll hand over to you to introduce your talk.
Thank you so much for such a kind introduction. Hello, everyone. I wanted to talk to you about FPGA Accelerated Computing. I will share two examples today, which I and my team have been developing for customers. So this is something very real, first-hand experience, and just wanted to share, how exciting FPGA Accelerated Computing can be. This is just a recap. So FPGAs are configurable and reconfigurable device. The major building blocks are the lookup tables that you can program for any combinatorial functions. Then you have flip-flops for building sequential logic. Then you have on-chip memory. Some of the lookup tables can be used as memory. And then you have dedicated ones we call block RAM and ultra RAM. And then you have these DSP engines, which are sort of like ALUs, so multiply, add, accumulate. So as an example, one of the FPGA used in AWS F1 has 1.2 million lots, 2.4 million flip-flops, and 345 megabit on-chip memory, and 6,800 DSP engines, right? So you can see like this is a really very powerful processing machine. And the region FPGAs do well, as you'll see in the examples that I'll share, because you can choose to implement depending upon your application. You can say, hey, I want only 7-bit integer. And you can have that, right? And very efficient. 13-bit, you can have it. Then you're not limited to the memory hierarchy that CPUs and GPUs have fixed. You can build your own hierarchy. And then, of course, since you are implementing the logic, you can have custom data paths, right? There are some of the things that helps. There are additional things that helps, which are like, and that actually is related with custom data path, is you can let the one block stream to the other without needing to go to the DDR and back. That would be needed for CPU, especially when you have large amount of data that you cannot just cache it in your CPU. All right, so this is just a recap. This is another slide for recap. So FPGA programming has gotten a lot easier. Starting with schematics, now we are not only doing this software defined for software developer, we're also sort of putting together frameworks so that you can actually use just Python and some API calls to this program and use it. So it's all good. So let me jump into the example, which is the main topic that I want to discuss today. So the first example that I want to discuss is anti-money laundering watchlist management. So today what happens is whenever there is a banking transaction, the different governments have different laws. They require the banks in that geography or in that country to report on a watch list, right? Or actually check the transfer against a watch list. Watch lists are the people which are the bad players, right? Bad actors. They're doing some sort of money laundering. They are criminals. So they have a database, right? So the way watchlist management works today is right now it's run as a batch process, and it takes like more than an hour. That's what a lot of banks we are working with tells us. And then when they detect some bad actor, they have actually let the transaction happen already. And then later on, they have to sort of follow. And the second thing is that even if you're a good actor, you have to wait for an hour, So that sort of makes the good actors sort of bear the burden or the cost of checking against the bad actor. So that's why these banks are interested in sort of accelerating it. So what it involves is you have these this is just an example. You have this bank code, and there are like 30 in this particular example. There are lots of bank names. There are around 10,000. And there are like 6 million names of the people who are the bad actors, right? Who are in the watch list. And then in the transaction description, there are certain keywords they use. So we have to look for certain keywords, right? Like drug, smuggling, all that stuff. So when a transaction comes, it comes in a particular format. It's called Swift format. And then that needs to be checked very quickly within milliseconds. And then we need to either deny the transaction, then we generate an output called KO, or else just allow it. Okay. So that's sort of like the application. Any questions? All right, looks like I explained it well. You guys can hear me fine, right?
Yes, we can.
Yeah.
All right.
Okay,
Yes.
all right. Just wanted to make sure that.
Yes.
Okay, excellent. All right. So how do you build such an application on FPGA? So I'm going to walk you through the steps, right? So first thing we do is we identify the kernels or the functions which we should try to accelerate on FPGA, right? So you try to see which one is taking most amount of time. You do some analysis, right? Little bit. So for this particular one, when we did the analysis, what we found was a string equal and the substring for the keywords, right? Substring match. If we did on CPU, it didn't cost much. And we could do that in parallel to while FPGA was doing the heavy lifting. And the heavy lifting with like 6 million names of the bad actors and 10,000 names of the bank. And there they can misspell it, right, on purpose. So we have to do fuzzy match. So it's not an exact match. So we do Levenstein's distance there. And this is what the transaction looks like. Output to, so basically, this is like the result of the transaction, right? So you say these are the different runs we have done. So this is transaction number 1, transaction number 2. KO means this was denied, some kind of description, and this sort of how much time it took, right? That's how it reports from that FPGA, right? So this we decided that this is going to go on FPGA, this will stay on CPU. So that's like first step, right? And then you decide on what kind of output you want. So once that spec is done, then you start thinking, hey, what will go on FPGA? How should I leverage the entire fabric to get maximum processing going in parallel, and we can do the fastest possible, right? So in this particular scenario, we looked at we implemented it on AWS F1 as well as on U50. So we analyzed for both and similar implementation almost. So what we decided was that we'll have, we could fit processing unit, 8 of processing units. And then each processing unit would have 10 sort of edit distance, or actually Levenstein distance calculation, right? And then we will take their sort of, so this, we divide up the basically list, so you have 6 million, so we'll divide up the 6 million among, so 10 multiplied by 8, around 80, right? So 80 fuzzy match kernel, and then we'll get the result, and then we'll just be able to, if we get the match, we already know that we no longer need to check on others, so we can abort others, right? So you organize your computing, you just figure that out. This is what I'll do. And this you do by looking at, you can write one kernel and implement it, see how many resources it took. Then you can roughly get an idea how many I can fit on that FPGA. Okay. All right. So in this particular case, one kernel had these 80 fuzzy match functions, and then we were able to fit 2 of these. So there were 2 compute units we could fit one FPGA. All right. Next. Now you can, so once you figured out that this is how your architecture is, you take your kernel and you start coding in HLS C++. So this is an sort of like an example of what the kernel looks like, right? All right, so you can see it's just like C++. I've got a templatized function here, and then I make certain instances of that here, and then here is another templatized function, right? And then this guy then makes is reading the data from a CSV format. It's doing some sort of filtering, and then it's calculating edit distance and collect. So it's very easy to read and very easy to maintain. You will love HLS coding. All right, next. So that part will go on FPGA, right? Now, when the FPGA gives the result, we first of all, we need to enqueue to the FPGA and then get the result, and we have to do rest of the processing of substring matching, on the on CPU, right, in parallel. So this just gives you an example of host code, right, that uses the XRT to do and invoke these kernels, So there's some higher level functions we have written, which will, underneath will call make XRT calls. Okay. All right. Now what you can do is now you compile the portion that will go on FPGA using V++, compiler, just like G++, right? And you can see it's similar to G++ compilation, although it takes longer, a lot longer, for a good reason, right? And the host code side, it's a pure C++ code, right? So you just basically run G++. So you get a shared library here, and you get a XCL bin here. So this XCL bin will go on FPGA. This shared library will run on CPU. And now if you want to use it in your application, let's say you are a bank, you already have an application, right? Some Oracle-based application, for example. Then you can write some sort of user-defined function or some kind of plugin. You can just include the .h file that we provide, right? And you just initialize it, and then it will link with this AML.so, right? Which has, which is the host code that will talk to runtime, and then will talk to FPGA. And the way we have built this SO, it can support multiple cards. Meaning, like if you have U50, it will work with same SO will work with 50, same SO will work with F1.2. In fact, we have support right now for this application for U250, F1, 200, U200, and U50. All right, so we're trying to make it more like how a software developer is used to, working, right? So it's easier to use FPGA. Now, once that is there, you have a running application. So so that there's no basically hiccup while running the demo, I just did a recording. I had done this recording for DAC presentation. So I'm just going to play that. I will show loading of 6 million records of watch list into FPGA memory, followed by running check on 100 banking transactions against this watch list, and then I will present the results. The watch list consists of 30 bank codes, around 9,500 names of the banks, 6 million names of the people, and 148 stop keywords. Let's get to running the demo. This window shows names of the banks who are in the watch list. This window shows codes of the bank who are in the watch list. This window shows stop keywords that we need to be looking for in each transaction. And this window shows names of the people in the watch list. These 4 data set comprises the watch list. Now this window shows 100 transactions that will be checking against that watch list. Each transaction has several fields. A subset of the fields of each banking transaction needs to be checked against the watch list. Some of the fields will be direct string matched, some will be substring matched, and some will be edit distance matched. Now let's get to running the demo. I've got a host code executable called test already built, and I've got the necessary XCL bin, which is the bit stream going on FPGA already built. And I'll provide this directory where my watch list is. And -C0 is for running on FPGA, not running on CPU. So I'm going to run it. This is going to load the watch list in x86 memory, then send it to FPGA memory. Once that is sent, then for every transaction, data need not be resent again. It is not sent again. This transaction will just run. And then transaction running is very, very fast. As you can see, running each transaction took on average 8 milliseconds, which is very fast. The first transaction takes a little longer, 24 milliseconds, because some housekeeping needs to be done. The subsequent ones run very, very, very fast. Here you can see OK means the transaction did not have any match against the watch list. KO means the transaction had a match against the watch list. So this transaction will be denied. Now, if I were to run the same transaction using only CPU, then it's going to be very slow. Using one core of CPU, I ran it just before starting this recording of the demo, and it took more than 5,000 milliseconds. Now let's compare the results. As you saw, FPGA is around 650x faster compared to one core of Intel Xeon E5. Now, if you were to add more cores and parallelize the application, you'll get some reduction, but Amdahl's law will kick in. In addition, the memory bandwidth to these multiple cores will become a problem. So after a while, we'll hit a wall and it won't go down. It will never get down to 8.5 milliseconds, which is needed for this kind of real-time banking transaction check. Thank you for watching the demo. So in summary, right, so the FPGAs are truly massively parallel customizable device, right? Programming FPGA is not really that hard. And for the AWS, I showed 650x faster, but I also did measurement on a local machine with Alveo U50. U50 has HBM, so it's even faster. So it took only 7 milliseconds as opposed to 8.5 milliseconds. And I did parallelize on this machine. It has got 48 core Intel Xeon server. I did full sort of multi-threading, and it could get down to, as I had predicted, only 1400 milliseconds. If you compare the power and cost, and then you just factor in all of that, you multiply how much advantage you have on the power and cost, you get around 3200x savings over CPU by using a card like Alveo U50. Any other question? I was lenient here. I measured it. It was like 25 watt, right? Power is like hugely less. And if you go to the ID rack and measure the power of the server, it's like huge. I just quoted here what is sort of related. All right. So there's one area, and this is one of my main responsibility, in fact, data analytics acceleration. So we have several engagements underway for accelerating the database analytics using FPGAs, and we're seeing like really good potential there. So if you just look at the database landscape, so this is taken from William Blair, right? They had a very good report published, so I read that and I just took this picture from there. So you have non-relational databases, which are also called sort of like big data. And then you have relational database, RDBMS, right? Which are basically tables, right? Rows and columns. Operational is where you have, you're doing transactional, like when you're doing banking, right? So you write, read, basically. And analytics is when later on you're analyzing it, basically. Like you have sales data, which can be operational too, but later on you're trying to analyze. You have lots of logs, application logs. You have HR related data, sales channel data, all that stuff, right? There's all kind of data where you want to run some analytics and gain some intelligence, right? So that's sort of analytics, right? So where we found that when it's transactional, then it is not where FPGA, this particular quadrant is not where FPGA provides great value, because these are typically update related, and things are very optimally written for CPU already. So we don't play there. But analytics, and also if you're doing big data, non-relational ones, even in operational, you could accelerate quite a bit using FPGA. So this picture sort of now drills into the data analytics part. It removes the operational part, just this particular column, right? This is what we're going to focus. So you may have heard things like Apache Hadoop, MapReduce, Apache Spark, etc. Like these are like distributed query engines, right? And then you can run analytics. You can do extraction, transform, load, extraction, load, transform. You can generate report. You can run some query, right? And you can, these days also there are streaming sources. So there are frameworks like Apache Flink, or even Apache structured streaming, Apache Spark structured streaming, right? So that there is something called Kafka, right? You can use that in conjunction with a query engine to do like live data sort of analysis, right? If you don't have streaming and lots of data gets produced, they typically get dumped in some cheap storage, and there are like in terabyte size, right? And they are so huge, and they are not in a native database format. So they'll typically be in semi-structured or unstructured, like JSON, CSV, Parquet sort of semi-structured, Avro, or it can be some proprietary format too, right? And these are some of the storages they'll use it. Now, later on, when you want to analyze it, you can basically run extraction, transform, load, or extraction, load, and transform, and get into some native proper database, right? Which could be a columnar database, or it could be RDBMS, doesn't matter. But for analytics, typically you don't do RDBMS, you do columnar because your queries run much faster. So once you have ingested that into some native database suitable for analytics, examples are like Cassandra or Google Colossus, etc., right? Even Redshift. Then that's called data warehouse, right? And then your queries on that ingested data will run much faster. But you'll never have capacity or the bandwidth or manpower to get all these data here. There's a lot of work, right? So sometimes you directly run here. And when you directly run, typically if you're doing machine learning training, you will directly run on this unclean data, right? And then query will extract the data and it will train the machine learning models, right? So what companies like Amazon have started to do, you might have heard of an instance called Redshift Aqua. They've started adding caching nodes here, right? So where they will actually do parsing, some sort of filtering, scanning, etc., using FPGAs, and then they'll have data cached. So if you directly run on this unstructured data, it doesn't have to do parsing again and again. It doesn't have to fetch that data in an expensive way again and again. So your query runs sort of faster. Okay. So this is called federated query. This is native query. This is streaming query. So you can see the opportunities where we have found FPGAs really shine. Or if you have any specific algorithm, like the demo I'm going to show, this is for recommendation engine we call cosine similarity calculation, right? Then from the query, when you're building that algorithm, instead of having your query as an algorithm, you can say, hey, just call this pre-built algorithm FPGA, right? Very easy way to accelerate your analytics. You can have some tighter integration with Kafka and Flink and Apache Spark structured streaming to get streaming acceleration. You can do all these things for the caching node. And if you want to do the native one, then in native one, what happens is they split up the data and the data stays on the local disk so that all these compute nodes can compute in parallel. But sometimes as the query proceeds, there needs to be shuffled. So then some disk IO is involved, network IO is involved. So FPGA offers things like SmartNIC, where you can do something called onload to bypass the CPU and directly move this data from here to the memory of other CPU. Things like that you could deploy to get your native acceleration going. Okay, looks like no question. So I go to next. All right, so the example I'm going to share with you is this is one of a large healthcare company in the United States. They are working with us. They gave us this problem that when either a doctor is seeing a patient or some patient calls the insurance company and they have to make decisions about what care to provide to the customer. They want to quickly find top 100 customers or top 100 patients like the one they are addressing right now to optimize their cost, right? So if something has worked for the other one, they can get that data and then they can allow either doctor to make decision, or if it's related to the home care and certain medications, etc., the insurance company can optimize that basically. So how do we sort of build a solution, right? So we identify analytics to be accelerated. So in this case, we said we'll use cosine similarity algorithm to find similar patients / customers, right? Patients are customers in this case. Implement the FPGA version of it, right? Write hash code, package the library. Then use user-defined function to directly integrate the database. So in this case, we used graph. They were actually our healthcare company was using a graph database called Tiger Graph. So they allow user-defined functions to integrate C++ into their code. So graph databases have started to use something called GSQL, GraphSQL, which is easier to sort of query for the graph databases. It's SQL-like, but it's a little different. And then you can use FPGA either in cloud or you can buy U50 to insert your server. You install Xilinx XRT and you can run the accelerated application. Okay, these are sort of like step to solution. And how is it built? So this is your target platform, U50, U280, it could be F1 also, and in XRT. And this allows you to develop the kernel. Then there is this linear algebra library that we provide free of cost, right? It's on GitHub. And using this, we also built the cosine similarity that we have made public as well on GitHub. And then you have the Tiger Graph database. So that's how it sort of integrates seamlessly, right? So I'm going to show something, a very seamless integration. You'll be amazed how basically cleanly and tightly it can be integrated with the database to achieve massive acceleration. So I'm going to play another demo video.
Today I'm going to demonstrate enablement of real-time healthcare using Tiger Graph database and Xilinx Alveo U50. One of the world's largest healthcare companies created a challenge called Customers Like Me that asked vendors to help them compare any given customer to a database of around 50 million customers in real time, to be precise in under 100 milliseconds. Xilinx worked with Tiger Graph, the world's fastest parallel graph database analytics platform, to build a joint solution which proved to be the highest performant and the lowest cost solution. Today, I'm going to demonstrate calculation of customer like me for 1.5 million customers on a high-end HPE DL385 Gen 10 Plus server, which has total of 128 physical cores and 256 GB of RAM. One Xilinx Alveo U50 card has been plugged into one of its PCI slots. Let's get to the demo. The load window shows CSV files. This is the data set that we'll be using. This data set has been generated by a tool called Cynthia. One of the files, patient.csv, is shown here. We'll be calculating cosine similarity for patient named Petrina 721, Bergnom 523. To calculate similarity, first, these CSV files need to be ingested into TigerGraph. TigerGraph supports a SQL-like language called GSQL. I have written GSQL to create a schema and then load these CSV files using that schema into the TigerGraph database. That has already been accomplished. In addition, I have written base.gsql and query.sql, which define multiple GSQL queries to traverse the database and construct patient vectors. I have already run a query called load Alveo that is defined in query.gsql, and it traverses the graph database, constructs the vectors, and saves the vectors into high bandwidth memory of Alveo U50. So to demonstrate the run, now I can simply run cosine sim SSAV, which will give me the cosine sim using Alveo U50. And to compare the performance, I can run cosine sim SSTG cached, which runs on CPU only. Just to show you what the queries look like, this is what cosine sim SSTG cached query looks like. This is a CPU only query, does not use Alveo U50. And this is what cosine sim SSAV query looks like. This query goes into the Xilinx runtime library and reaches onto Alveo U50, does the calculation there, and gets the data back and results it. So let's get to the demo. So I can simply run it to calculate, and you can see it's blazingly fast. It took only 10 milliseconds. Now, if I were to run the same query on CPU only, it's going to take a long time. So that's why I started this run sooner. It has finished now. You can see that the pure time to compute is 422 milliseconds. This time I'm excluding because this time is when the vectors are being constructed and cast in the vertices. I did an experiment by varying the size of the patient and measuring both the CPU time and the Alveo U50 time and plotted it on a graph. An interesting pattern emerged. As the number of patients grows, Alveo U50 time stays under 35 milliseconds, whereas the CPU time increases exponentially. This can be explained by the fact that Amdahl's laws kicks in, as well as not all cores can be served at a fast speed from the system memory. In conclusion, Alveo U50 could calculate the top 100 similar customer/patient in less than 100 milliseconds, that is real time, whereas a very high-end server costing more than $20,000 could not compute it in real time. To meet the original challenge of calculating against 50 million patients, we can put 5 Alveo U50 cards in this server, and we can compute the cosine similarity in under 50 milliseconds, to be precise, around 40 milliseconds. Whereas to calculate the same using CPU only, using 128 cores this server, it will take more than 16,000 milliseconds, which is 400x slower. Thank you for watching this demo. If you would like to achieve similar kind of
So just to sum it up, right? You saw for data analytics, it can be integrated very seamlessly. So from the SQL, it goes to the user-defined function C++. From the C++, it goes to the shared library and to XRT. So basically, to the user, it will feel like, it's just like integrated database. They don't even know about FPGAs. And then if you look at the power, I went and checked the power. This server is massive, right? As you can see, 128 core. This is one of the latest, right? And I checked in the ILO that you can use to access the machine to power down, etc. I checked, like, it was 750 watt. In fact, it was more. Whereas the Alveo is just 25 watt, So basically, the idea is that if you have this particular application that you want available, and for that, if you are going to buy an expensive server, so it's a no-brainer that buy a cheap machine and buy LUU50, and then you'll save lots of money and power a little bit faster, right? That's what we're trying to say here. Yeah, I think that's all I had in terms of presentation. So I think we can have sort of open discussions, questions.